In this video, I'll be doing some formulations for the linear programming problem, and this is a practice sheet. This practice sheet I've already started in my last video, and in which I have covered question number 1, 2 and 3. So for these 3 questions, you can watch the previous videos and the link is added in the description. In this current video, I'll be solving the remaining problem, question number 4, 5, 6, 7, 8 and then question number 9. So let's get started with the question number 4. So in question number 4, this asks a manufacturing company has a contract to deliver 100, 250, 190, 140, 220 and 110 home windows over the next 6 months. And production cost per window varies by period and it's estimated to be this much. So this is the cost given for the windows over the next 6 months. To take advantage of the fluctuation in manufacturing cost, company can produce more windows than needed in a given month. Since this is the given requirement, but it says that we can have more windows and this will hold the extra unit delivery in later months. So the extra windows that are being produced, they can be saved for the later use. This will incur a storage cost at the rate $8 per month. Formulate the problem as a linear programming problem. So to formulate the problem, let me to first take the decision variable. Let xi, this is the number of units of windows produced in the month ith. Produced in the ith month. So because that has to be produced over the next 6 months. So let's say first month, second month, third month and 6th month. And then we can take Ni. This is the number of units of windows left at the end of month I. Because we said that we can produce more windows, and if at all there is some remaining window which we will carry forward for the next month, that will denoted by the factor Ni. That will be denoted by the variable Ni. Now I want to minimize the total cost because the cost is given. The cost of manufacturing is given, and then there is a storage cost also. You can see that the production cost is given and there is a storage cost. So since the cost is given, so we obviously want to minimize the total cost. So we will say minimize Z equal to. Now there are 2 costs involved in our problem. One is the production cost and another is the holding cost. So holding, that means the windows that are we keeping or storing for the uses in the next month. So I will first write the production cost and then I will write the storage cost. So this I will say this is storage cost and here I will write the production cost, and both obviously has to be added. Now for the production cost, this is very simple. We have taken xi and we know that there I lying between 1 and 6. There are 6 months for which we are talking. So we will simply multiply 50 times x1. This is per unit window cost, and if x1 is the units of window produced in the first month, then we are multiplying 50 into x1. Then we'll take the another cost, that is 45 into x2, then followed by the next one which is 55 into x3 plus 48 into x4 and then plus 52 into x5, and I will add one more, that is 50 into x to the power 6, x6. Now we need to add the storage cost, and for the storage cost we can say this is $8 per window per month. So this is a fixed cost, and so I will take plus 8 times n1 plus n2 up till n6. Okay, so that becomes the objective function. What is the condition? Condition is that the windows that we have produced in the first month, that is x1. So we have selected the decision variable x1. This is the number of windows produced in the ith month. Now x1, what is the requirement? We see the requirement, we need to deliver 100 windows. And we said in the problem that the company can manufacture more than 100 windows. So what we will say, x1 has to be 100 plus if company produced extra window in the first month. So this will become month 1. We may produce or we may not. So that n1 decision variable will also be greater than equal to 0. But let's say we are assuming that there are some windows which are available in the first month and this number exceeds than 100, then this n1 has to be added in 100 and that becomes the total number of windows produced in the first month. Now similarly, The month 2, we will carry on these windows which are remaining. So that is N1 plus the more that are produced in this month, that is month 2. This should be 250 because that's how we need to deliver the windows, which is here 250. Plus if some windows are remaining from here, the total. So if this number N1 plus X2 exceed than 250, then that number will be denoted by N2, and these N2 windows we will carry it in the next month. So this will be for the month 2. Now similarly, if I look at the third month, so in the third month, we first see which are the windows that are coming from the month 2, that is N2, plus the new windows that we are forming in this month 3, that is X3. This should be 190, so we will write 190, plus similarly, if this number total is 190, this N3 is 0, otherwise if there is any remaining number of the windows, we will carry forward it in the next month, N3. And now for the month 4, we can see again on the same lines for the month 4. First, look at the windows that are being carried forward, that is N3, plus the number of windows that are taken from the 4th month. So the variable is Xi, so we will add X4. This should satisfy the demand, which is 140, which are the window that has to be delivered, plus the extra windows that will go forward to the next month, N4. Now similarly for the next one, N4 plus X5, this should satisfy the demand, that is 220, and plus we will have N5, so this is month 5. Then we will have N5 carry forward, and finally the windows that are produced in the last month. So this 6 means that we are producing in the last month, 6th month, and this whole process we are doing it for 6 months. Now last month has to ensure that all the windows are occupied, so we will only produce, because this is holding capacity is only for the 6th month. This whole problem in which we are carrying forward, this is for 6 months. So last month we will only produce that much window which satisfies this equation, N5 plus X6 equal to 110. So there is no holding capacity for the 7th month. So that means in the 6th month, we want to ensure that all the stock is completely moved out from the storage house. So this will become month 6. And as we know that all the decision variable that we use in the problem, Xi, they should be greater than 0, and Ni is greater than equal to 0. So this becomes the formulation of this problem number 4. Now in question number 5, John must work at least 20 hours a week. So that is the at least criteria. To supplement his income while attending school, he has the opportunity to work in 2 retail stores. In store 1, he can work between 5 and 12 hours a week. So let's say this is the working time. So he can work between 5 and 12. So that is one condition. And it is also said that John must work at least 20 hours. So this should be greater than or equal to 20. I will see how we can choose the variable. Let me just first write down the data. He can work between 5 to 12, that we have already considered. And in store, so this was for store 1. And for the store 2, he can work between 6 and 10 hours. So this will be between 6 and 10 hours. Both store pay same hourly wages. So the wages rate are same. In deciding how many hours to work in each store. Now this is the decision criteria, because the number of hours working in each store is not same, although the wage price is same. So what should be our decision variable? We should choose, let's say X1. This is the number of hours John work in store 1. Okay, because that cannot be same, it's said in the problem. And then number of hours John work in store 2. So while finding the optimal solution, they may come out to be same, but right initially while deciding, it is not said that he is working in the equal number of hours. So the question is that the person has to still decide how many hours to work in each store, which means initially we must need to take that these two are different decision variable. This number may be different, that the John may be working 10 hours here and 10 hours here, or 15 hours here and 5 years, considering that it has to be work at least 20 hours, or you may have any criteria like 20 hours working here and then 5 hours working here. So that's a secondary question while we search for the optimal solution. But currently we are simply interested in knowing the formulation. Let's move forward. John wants to base his decision on work stress. which are 8 and 6 respectively. So assume that total stress is proportional to total number of hours. So this means how much hours that he is working, that will depend on this work stress level, and determine how many hours John should work in each store. So let's talk about the objective function. Now objective function is minimization. Why minimize? Because you want to reduce the stress. John want to base his decision on work stress, which are 8 and 6, and these are proportional to the number of hours. So the more number of hours he is working, he is getting more stress. So which means we want to reduce the stress. So here you want to minimize 8 times x1. The John worked in the store 1, so number of hours, plus 6 times x2. So because it is proportional, so if we decrease this quantity proportionally, our objective function will decrease. Subject to, what are the constraint? Constraint is John should be greater than or equal to 5 while working in store 1. It should be less than or equal to 12. We can combinedly write this as 5 less than or equal to x less than or equal to 12. This is because of the store 1 constraint, because x1 is due to the store 1. And similarly, now I can write for store 2. For store 2, x2 is greater than or equal to 6 and x2 is less than or equal to 10. So this I can again combinedly write 6 less than or equal to x2 less than or equal to 10. This is due to store 2. And in total, whenever he is working, in total he has to work at least 20 hours a week. So which means there is one more constraint, x1 plus x2. This is total number of hours in both the store. This should be greater than or equal to 20. Okay, and then we take non-negative decision variable, either he is working or not working. So the number of hours cannot be negative, and so this becomes the formulation of the given problem. Now in question number 6, it says a metal slitting company cuts master rolls with width 200 centimeters into sub roll of small width. Customers specify that they need sub rolls of different width given in the following table. Width of sub roll in centimeters is given here and the numbers required are here. The objective is to use minimum number of master rolls to satisfy the customer orders, and I just simply want to formulate this as a linear programming problem. Now this is one of the problem that we consider as trim loss problem, and 2 problems of the similar type I have already covered in my previous videos. So link added in description. So for this problem I'm not explaining, simply rather I'm writing the solution part and just giving the main highlight. What the width is given to us, it's 200. Say for example you have a master roll something like this one, and here the width is 200. So this is 200 centimeter, and now we want to slit in a way in a smaller sub roll. So slitting is something like this one, and this width that we require is 35 or 80 or 90 or 120. This is the requirement, 90 or 120. Now how many of each roll do we require? That number is also given to us, number required. But there are different possible patterns in which we can cut this problem. So as I did in my earlier problems, I'm going to construct the different possible patterns. So let me to write possible patterns from the given width. So we know the total width given to us is 200 centimeters, and we want to divide it in the 35, 80, 90, 120. So that's the width of sub roll. We can write width of sub roll in which we want to slit it from the main roll, and these are the possible patterns that I'm writing, P1, P2, P3. We need to write all exhaustive pattern. We do not have a formula to tell you how many are these. Since I've already made, there are 8 possible exhaustive pattern. One has to try all the options. So for this one, what I did is 35. So I've taken out 5 rows. So and then I've taken zeros from here, and if I multiply 35 by 5, I notice that this is 175. So total is 200. That means 25 is the wastage. So for example, if this was the sub roll and I have cut it all 35, 35, 35, I can take 5 sub roll like this one. This is one sub roll. Then I'll take another sub roll, third, fourth, fifth, and the remaining portion, this remaining portion would be considered as a wastage, and this wastage width is 25. Now, but the question does not ask us about the wastage, because it simply says in the objective function you want to minimize the total number of master roll. So I'm not calculating this last one, but one can see immediately that the wastage has to be definitely less than the smallest sub role that we require, 35. Now somebody cannot take a pattern in which the wastage is 40, because 40 cannot be a wastage. Out of 40 we can definitely take 135 role. So the wastage would be considered only 5 centimeter. So keeping in this mind, I will create all other possible patterns, 3010, 2001, and here I can have 0110. We can have one possibility 0101. We can have one more possibility 1200. We can have 0020, 3100. Now one can find the corresponding wastage quantity as well, and we require the number required with us for each of these sub role is given to us in the problem. And so I'll write this number here, that is 100, 90, 400, 800. So now we have a complete understanding of the question. We have the possible patterns, we have the width of sub role that is required, and we require the total number. So this 35 sub role can come from the different possible patterns. Similarly 80 can come from different possible patterns. So I will now write the formulation. Let xi, this be the number of roles, or you can say sub roles on patterns, on pattern pi. Okay, so we can add it sub role. Now I want to minimize these sub role. So we minimize, how many possible patterns we have? 8. So obviously there are 8 possible. So we may consider these like as a unit. So if we consider 111 from each pattern, so these may be considered as unit number of rows on pattern pi. Subject to, now if you look at first pattern, we can get 5 on the first pattern. So if x1 is the unit of the p1, which is the unit rows scattered on the pattern p1, so first will give me 5x1 plus 3x2. So you can read it row wise, and you know the desired number also that we require, plus 2x3 plus x6 plus 3 times x8 equal to 100. There are many quantities 0 that I have not written, like 0 into x4 plus 0 into x5 and then 0 into x7. Then we look at the second row to get the 80s. So this will give me simply x4. Since you can see the first 3 are 0. And so we have x4 plus x5 plus 2x6 plus x8 equal to 90. Then we got x2 plus x4 plus 2 times x7 equal to 400. And then we have x3 plus x5 equal to 800. And all the decision variables are greater than or equal to 0. So that completes the formulation of this problem. So we have decision variable, we have objective function, we got constraints, and we got non-negative restrictions. In problem number 7, a company has 2 grades of inspector, 1 and 2, who are to be assigned for a quality control inspection. It is required that at least 2000 pieces be inspected per 8 hours a day. Grade 1 inspector can check pieces at the rate of 50 per hour with an accuracy of 97%, and grade 2 inspector can check pieces at the rate of 40 per hour with an accuracy of 95%. The wage rate of grade 1 inspector is rupees 4.5 per hour, and that of grade 2 inspector is rupees 2.5 per hour. So their wage rates are different. So maybe we can just start the problem like grade 1 inspector, and then we have on one side grade 2 inspector. This wage price is 4.5 rupees, and here the wage rate is 2.5. It is said that the total pieces are to be checked this one, and each inspector check pieces, they check 50 per hour. This is the data given to us. Grade 2 inspector check the 40 pieces per hour, and here the accuracy level is 97%. Here the accuracy level is 95%. That means there is a possibility of 0.03 error, and here 0.05 error. Each time an error is made, the cost to the company is rupees 2. So this is error cost, and this is rupees 2 for both the grade inspectors. Formulate the problem, and we do not want to solve, so that minimize the total cost of the inspection. So for this one, I will take the decision variable as let x1. This is the number of grade 1 inspectors, and x2 is the number of grade 2 inspectors. So we want to minimize the total cost to the company. So we will say minimize Z. this is equal to, the cost of the grade 1 inspector is 4.5 into x1. This is per hour cost, and plus 2.5 into x2. Plus each time they make an error. So for the error also we have the cost. So this is the normal cost. We can say cost per hour. If you wish, we can simply say that we have calculated cost per 8 hours, and if we want to calculate cost per 8 hours, we can then further multiply it by 8. But currently I am calculating this cost per hour. And for the error cost, so that is again an addition, that means plus 2 times the error cost. Error, the first grade inspector error is 0.03 because the accuracy is 97%. So this is the error. And the number of pieces are checking per hour is 50. This is for 1 grade inspector and for x1 grade inspectors. Plus similarly for grade 2, 2 into 0.05 into 40 pieces per hour into x2. This is for grade 2. So that becomes the total cost which has to be minimized. We can say this is cost of error of grade 1 inspector, and similarly this one is for grade 2 inspector. Now this I've calculated total cost per hour, and as I've said, this total cost that I've calculated, this is per hour, and if I multiply this by 8, I can say that I'm calculating it for 8 hours, but it is not said somewhere in the problem that it is for 8 hours, so we will not consider 8 at this moment. I'm calculated the cost per hour. Now what are the constraints? For the constraint, the first condition says that total pieces has to be checked 2000 per 8 hour day. Now here it is mentioned. So one inspector check 50 pieces and x1 inspector will check 15 to x1, and in 8 hours they will check 88 into 15 to x1. This is by grade 1 inspector. Plus 40 pieces are checked by grade 2 inspector. So x2 are the grade 2 inspector, the number of grade 2 inspector. This much pieces will be checked per hour, and then we are checking it 8 hours. That means we are multiplying by 8. This should be greater than or equal to 2000. That is one constraint. It is also said that in the second last line, the company has availability of inspection job 10 grade 1 and 5 grade 2. So x1, which is grade 1 inspector, will not exceed 10, and x2, which is the grade 2 inspector, the availability for them is 5, and we can take that both x1 x2, this is greater than or equal to 0. So this becomes the formulation where we have an objective function, we got constraints, and we have non-negative restrictions. Now in question number 8, it asks, a company produces 2 types of hats. Type 1 required twice as much as labor time as type 2. So one of the starting criteria that we can write here for is the type 1 and type 2. So there are 2 types of the hat that problem is talking about. And if type 2 takes tea time, then type 1 take twice of tea time. Type 1 requires twice as much as labor time as type 2 alone. If all the labor time is dedicated to type 2 alone, so that means if all time is given here and we are not utilizing any time for type 1, company can produce 400 hats in total of type 2 per day, and respective market limits for 2 types are 150 and 250. So for this we will have 150, we will not make them more than 150, and for this we will not make them 200 hats. Profits are given for each hat as rupees 8 for type 1 hat and rupees 5 for type 2 hat. So this is the profit given to us. We want to find the optimal number of hats to be prepared so as to maximize the company's profit. So here the question says optimal number. So basically it is asking for the solution part as well, but I am currently making only the formulation. So for the formulation, since profit is given, I am going to first choose objective function as maximization. So I will maximize z equal to 8 times x1 plus 5 times x2, where what is x1, x2? x1 is the number of hats of type 1 and x2, this is the number of hats of type 2. So this is the objective function. Constraint. Now constraint, it says that it says about the market limit. So x1 will not exceed 150 because of the market limits capacity that's given to us. This will not exceed 200, and we also know that there are non-negative restriction that x1 is greater than equal to 0 and x2 is greater than equal to 0. So the hats are produced at least, or minimum value they can take 0 if one of the type of the hat we have not produced. Now one of the constraint that take double time. So for this we have been given a condition that if all the times are given to hat of the type 2, so we will say 400 hats of type 2 are made, let's say, in t time, and t time is the complete time. This is the complete time available in day. Okay, so if the total time is given in to the hats of type 2, we can make 400 hats. So this means one hat of type 2 will be made in t by 400 time. So this is, I have calculated the time of one hat, and we want to build x2 hats. We want to produce x2 hats of type 2. So it will take the time t by 400 into x2. So this is the time that is being taken by the x2 hat which have to be produced for the type 2. Now on the similar line, once I calculated one hat time, so now from here I can say one hat of type 1 will take the double the time. This time I already know one hat of type 2 will take t by 400. This is the time. So it will take double of this time, that is twice of t by 400 time, which means it is 2t by 400. So this is for one hat. So now for x1 hats of type 1, we will take 2 times t x1 by 400. So now we have a time for x1 hat and we have a time for x2 hat, and we know the total time initially that we have taken was t time. So for this, if I look this as a constraint, what I will get, 2 times x1 by 400 plus t times x2 by 400. This is the time for x1 hat. Time for x2 hat will not exceed the total time. And we see that t is appearing on both the sides, so t get cancelled, and taking 400 on the other side, I will get 2x1 plus x2 is less than or equal to 400. So that becomes a constraint. So here if I look at the problem, we got this as objective function, we got these as constraints, and we got the third part as non-negative restriction. So this becomes the formulation of the given problem. Now in this last problem of question number 9, Readymix produce both interior and exterior paints from two raw material M1 and M2. So there are two type of the paints. One is interior paint and another is exterior paint. So let's take the decision variable as per the paint requirement, because this is what we are constructing. Let x1, this is the tons of exterior paint, and x2, this is the tons of interior paint. So we can see the data is given in tons. So this is how I have taken the decision variable in tons. So units are basically in tons. Now it says that for this one I have taken x1, and for interior I have taken x2. And for constructing the exterior paint x1, I require the raw material M1 and M2, and the data is given this one. And this is the daily profit given to us in tons, thousands of dollars. And this is for x2, and daily availability is here. So if I look as an exterior paint, this is the requirement, but this is the cost. So I cannot construct a constraint like vertically, because on this side I have a cost, and here this is the units of the raw material. So I have to look vertically for the data, horizontally for the data. If I look like this one, raw material M1, which is consumed by the product x1, exterior paint, and for interior paint the availability is 24. So that will construct my first constraint. So we will say 6 times x1 plus 4 times x2 will not exceed 24. So on right hand side also we have tons, we have units of material available. On left hand side also, this is the material consumed while making exterior paint, this is the material consumed while making interior paint, and this is the availability. And so we have now the second constraint, which is this one. for the material M2. So we will have x1 plus 2x2 less than or equal to 6. So this comes from these two data. We also have objective function, and for the objective function, since this is profit, so obviously we want to maximize z equal to 5 times x1 plus 4 times x2. Now we have written the data till this one. Let's see what is written in the last paragraph. A market survey indicates the daily demand for interior paint cannot exceed for the exterior paint by more than 1 ton. So which means the interior paint which is due to x2 will not exceed the exterior paint by more than 1 ton. So by more than 1. So I will add plus 1, and this will become the restriction on the x2 variable. So I may write this as minus x1 plus x2 less than or equal to 1. So that also becomes one of the constraint. It also says that also the maximum daily demand for interior paint is 2 tons. Interior paint is x2. So we will write x2 is less than or equal to 2. These are the conditions that we have translated into constraint. So we have now decision variable x1 greater than equal to 0 and x2 greater than equal to 0. So this gives the formulation for the given LPP.